All right, for this problem, we're going to be taking a look at non-standard conditions, and we know that normally standard conditions imply that we've got 25 degrees Celsius, 1 molar concentrations for our solutions, 1 atmosphere for our pressures, and so obviously, those standard conditions don't always apply. So we're going to take a look at how we deal with cell calculations and finding the cell potential or the cell voltage if we have non-standard conditions. So going back to what we learned in the last unit, we know that there's this equation for the Gibbs free energy at non-standard conditions, and that was this delta G equals delta G naught plus RT ln of Q, Q being the reaction quotient. So when I think about this reaction up here for the silver ions reacting with copper and forming copper ions and silver metal, again, when I go to write the Q, it's equal to the equilibrium constant expression. Remember that we don't include solid species, so I would rewrite this as concentration of Cu2 plus, that's my product concentration, divided by my reactant concentration, and again the solids are being left out, so the only thing that ends up being indicated in here is the solutions. And notice I am squaring this because there's a coefficient of 2 on the silver. Okay, so that's where the Q is going to come from, and we're given concentrations to plug into there. So this delta G equation, this is for non-standard conditions, and we now have this relationship that we just talked about for relating delta G naught to cell potential. And so reworking this, and you can look through the book for the derivation of that, or through the notes online, we end up with the Nernst equation. The Nernst equation, the version that I'm going to write down here, is basically simplified down so that we're getting the potential for the cell equal to E naught, so that was our standard potential at standard conditions, and 0.0592 divided by n being that number of electrons, moles of electrons transferred. And they've actually put this in terms of log instead of natural log, and again, you can look at the derivation in the book, but substituting in, this relationship for delta G, so this would be, the negative NF E naught going in here, and the negative NF E regular going in here, rearranging, doing some algebraic magic, and then simplifying down. Again, this is including the R value that's been multiplied in. This number is including a temperature of 298 Kelvin or 25 degrees Celsius. And again, they've converted this into, for whatever reason, that's the standard. They work in log instead of natural log when we're looking at, and again, this is called the Nernst equation. So basically then it's just a matter of plugging in. So we already have the E naught for this reaction. If we didn't already, then we would find that using the method we've already described. We know that there's 2 electrons transferred because we already analyzed this reaction and had put that in originally when we found our delta G naught before. And then Q, well, we can just plug in the concentrations they gave us. So we've got 0.045 molar for the copper and 0.010 molar for the silver, and again that's squared, and that's going to come out to 450. And so then it's just a matter of plugging into this equation here. So we've got 0.46. Again, this is in volts, which is well, joules per coulomb, but we'll leave it as volts because we're ending up with an Ecell. And 0.0592 divided by 2 log of 450. Solve all that, and you end up with 0.38 volts. Okay. So obviously we can see when we are looking at this non-standard conditions and we're dealing with Q, as my product concentration starts increasing, we know that the value of Q is going to be increasing, and that means then that this value of log is increasing. And so we're going to notice that our voltage is going down in the cell as the reaction progresses, and as our concentrations change, as I reduce the amount of reactant and as I increase the amount of product. And eventually, we will notice that we get to a point where the battery is said to be dead, meaning that we don't have any potential left once we've used up formed all the product we can and used up all the reactant.